class. Welcome to 7.3's lecture. This lecture is simplifying and combining radical expressions. Now, the definition for a simplified radical expression, the conditions that you need to follow, are on page 607. So if you don't already have an intuition for what it looks like for a radical expression to be completely simplified, there are 3 conditions, and those 3 conditions are listed on page 607. But you may just pick up what it looks like for an expression to be fully simplified through this lecture, but I would still urge you to check at the end of the lecture, check page 607 and look at those conditions to make sure that you understand them. Okay, so I want to start with the product rule. Here we have the product rule. The product rule says that if you have the nth root of the product of 2 factors, you can actually split those 2 factors up into their own radicals, and that these are equal. Let me give you a quick and easy example. Suppose you want to simplify the square root of 50. Well, 50 is the product of several different factors, right? You could do 2 and 25, 5 and 10. There's a variety of different ways to split up 50. But when it comes to simplifying radicals, we always want to ask ourselves, what is the biggest perfect square? I said perfect square in this case because this is a square root. What is the biggest perfect square that divides into 50? Now let's review those perfect squares. We have 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. 25. 25 is the biggest perfect square that divides into 50. So what that means is that we want to split 50 into 2 different radicals. And those 2 radicals are going to contain factors of 50. 50 splits into 25 times 2. So this is okay. You can do this. This is the product rule. So I am splitting 50 into 25 times 2. How is that helpful? Well, 25 is a perfect square, right? The square root of 25 is 5. And so here we have completely simplified this radical. Let's continue with another example. The square root of 45. What's the biggest perfect square that divides into 45? 9. That's right. So 9 divides into 45. And so I feel like I'm now doing an episode of Blue's Clues because I'm acting all by myself and I'm talking to the audience. So I watch a lot of Blue's Clues at home. I'll try not to go to that level. Anyway, 45 is 9 times 5, right? I split up 45. I need to have a perfect square. I call this first radical the perfect square house. That's not an official name. The perfect square house is only going to contain perfect squares. And we want the largest possible perfect square that divides into 45. The second radical I call the reject house. 5 is not a perfect square. It is rejected. It's pushed off. And so here I have the square root of 9 times the square root of 5. And of course, the square root of 9 simplifies. So the final simplified answer is 3 square root of 5. Okay, next example. Cube root of 54. So when you go to a higher root, instead of looking for perfect squares, you look for a perfect power that matches the number right here. Okay? So this number is 3, so what we're looking for are perfect cubes. If it were a fourth root, you would be looking for perfect fourth powers. So here we have a cube root, so we want to know the largest perfect cube that divides into 54. So what are those perfect cubes? Of course, 1 cubed is 1. That's not a very interesting perfect cube. 2 cubed is 8. 8 does not divide into 54. 3 cubed is 27, and 27 does divide into 54. So we can split this up. So here is my perfect cube house, and here is my reject house. I have split it up into 2 radicals. The cube root of 27 is 3. So the final simplified answer is 3 times the cube root of 2. Now, believe it or not, simplifying with variables is actually easier. That's because it can be kind of tricky to think about what divides into large numbers. So far, the numbers that I have used have been small examples, small numbers, right? 50, 54, 45, those all have factors that we can think about in our minds instead of having to use a calculator. You'll find that more of these examples are going to involve variables. Variables are actually simple. So let me show you how it works. Remember the analogy I told you about in the last lecture? Suppose Adam has 9 tickets, and to go on this ride, it cost 4 tickets. This is a fourth root. So how many times can Adam go on this ride? He can go on the ride 2 times, right? And then he'll have 1 leftover ticket. So what we want to do is we want to split this into 2 radicals, both with fourth roots. Do not forget that. You must continue with fourth roots if you have a fourth root problem. So don't just drop the 4. They have to stay in the problem. Okay, so let me start with the structure. Okay, so when Adam organizes his tickets, he might organize them into groups of 4 so that he can keep track of each group of 4 representing a ride that he gets to go on. So Adam would have 2 groups of 4, which would be 8. And then he has 1 leftover ticket, and so he holds it over here in his other hand. So you don't have to use this analogy, but if it's helpful, great. What about B? Let's make this Bob. Okay, Bob has 6 tickets. He can go on the ride only once, right? Because it takes 4 tickets to go on the ride. So Bob is going to put those 4 tickets in one hand. And the other 2 tickets are going to be held in the other hand as the leftover tickets that can't be used for this ride. Okay, so now we have separated into a perfect fourth power house and a reject house. And when we simplify this, it just goes back to how many times can Adam and Bob go on the rides. But the other way you can think of it, and this is actually less analogy, more math, just take the exponent and divide by this number right here, and you'll get your result. So 8 divided by 4 is 2. 4 divided by 4 is 1. You do not need to write b to the first power, just b is fine. Since this other radical cannot be simplified any further, we just copy as is. So we are left with a fully simplified radical. Okay, next example. Cube root of 297 b to the 4th power. Now, 297 is a pretty big number. That's pretty tricky. So you'll want to use your calculator to split up the number, and you may want to consider using a prime factorization tree. So you want to divide 297 by some numbers. It's an odd number, so it's not divisible by 2. How do we know if a number is divisible by 3? There is a special divisibility rule that works for 3, and it only works for 3, and there's one also similar to it that works for 9. But if you add up the digits, so 2 plus 9 plus 7, if you add up those digits, and the sum of those digits, in this case 18, is divisible by 3, then the entire number is divisible by 3. This divisibility trick only works for multiples of 3. And then the one for multiples of 9 is if the sum of the digits divide by 9. So as it turns out, since 18 is divisible by both 3 and 9, this number 297 is also divisible by 3 and 9. So what is 297 divided by 3? Well, so 297 is 3 shy of 300. So that would make it, instead of 3 times 100, 3 times 99. "99 splits into 9 times 11. And then I noticed something here. 9 times 3 is 27. And 27 is a perfect cube. So I have the perfect cube I was looking for. I dropped my lid and it's bothering me, so I'm picking it up. Aha, here I am. Okay, so let's come back to the problem over here. I'm on a learning curve too. I am learning to post online videos of myself, and so it's a new skill to learn how to film your own lectures. So hopefully I'll get better and better at this. I've learned to use the pause button to set up new examples. If you have some tips, let me know. My father already told me to quit cutting off my head in the frame. Okay, so here we have 27. 27 times 11. 27 is a perfect cube. Now for the variable, b to the 4th. So Bob has 4 tickets. It takes only 3 tickets to get on the ride. So Bob is going to put the 3 tickets in one hand. And the 1 ticket in the other hand. And now we have split up the radical into a perfect cube radical and a reject radical, right? A perfect cube house and a reject house. So the cube root of 27b cubed is simply 3b. And then you copy the other radical as is. Look, I copied the little 3 in here too. You must still copy those numbers that are inside the radical right there, okay? Let me point out for a second that this number inside the radical has a name. It's called the index. So I will try to use that more often. I've been trying to avoid too much heavy vocabulary for the sake of getting these lectures going, but this little number is called the index. So I may start referring to that as the index, and now you know what it is. All right, so next we're going to move on to the quotient rule. Just one. The quotient rule is very similar to the product rule. You can split a quotient into 2 separate radicals with the division sign in between them. So in the case of, oops, I put the nth root. Let me do the square root. That would be more practical here. Aha! The square root of 4 over 9 is going to be the square root of 4 divided by the square root of 9. The square root of 4 is 2. The square root of 9 is 3. And that's the use of the quotient rule. with the previous example, I went with the square root of 4 over 9 breaks into the square root of 4 over the square root of 9. I went from left to right. Now I am going to use the same rule from right to left. So here I have a square root that's already broken up into a radical divided by another radical. So this is going to be a lot more useful. We're going to go from the right to the left. We're going to simplify the fraction inside, and then we will simplify the resulting radical. So going from the right to the left, this is how we rewrite the radical. When drawing the radical symbol, make it big if you need to fit something big inside. Make sure it's really clear whether or not the denominator is included inside the radical. This radical goes down far enough that I have made it very clear that 5xy is part of this radical statement. Okay, now I'm going to simplify the fraction. 45 divided by 5 is 9. X cubed divided by x is x squared, and the y's cancel. Remember, do not cross out your work. If you must, use a highlighter, but otherwise it's better to use check marks. If you cross out your work, I will not be reading your work. 45 over 9 reduces to 3. Sorry, let me say that again. 45 divided by 5 reduces to 9. X cubed divided by x reduces to x squared. Y divided by y cancels entirely. So now the square root of 9x squared is pretty straightforward. Square root of 9 is 3. Square root of x squared is x. I want this radical to go far enough that it covers the x squared, but not so far that it covers the equal sign. So be careful with your use of notation. For my next two examples, I want to show you problems from the homework set. This is from MyOpenMath. This is question number 9. This is question number 19 of the version that I pulled up on my computer. Okay, so in both of these examples, we see simplifying a square root, simplifying a cube root. But both of these examples have something in common in that there is a number outside the radical. So what you do is you just let that number hang around until the very end, and then at the very end you multiply that -5 to the result. Here you multiply the 7 to the result. So let me work through these problems. You can see me work through them, and then you can, and then I will explain what I just did. Okay, here we go. Okay, now let me explain what I just did. So first, the square root of 125. 125 is 25 times 5. So I put the 25, which is a perfect square, in the first radical, and the leftover factor, in the second radical. So I have my perfect square house and my reject house. Then c to the 11th power splits into c to the 10th times c to the 1st. Remember that this exponent right here must be divisible by the index. So 10 divided by 2, the index of a square root is 2, gives you the quotient 5. So when I simplified 25c to the 10 power, I end up with 5 times c to the 5th. Notice the -5 hangs along for the ride. Okay? You just keep copying it from line to line. It's not until the final step that I then multiply negative 5 times 5c to the 5th power, and I end up with negative 25c to the 5th power times the square root of 5c. Now I will simplify question number 19. $625. I know that 625 is 25 times 25. So that means it is 5 to the 4th power. It may be even helpful to rewrite this as 5 to the 4th power, and then you can write 5 cubed here and 5 to the 1st there. So here's my suggestion. Take 625, use the prime factorization of 625, and rewrite 625 as 5 to the 4th power. Now we have 5 to the 4th power and x to the 14th power, so you can treat both of these the same way. Treat 5 and x both as variables. Okay, so 5 cubed, 5 to the 1st. Remember, anything here must have an exponent that's divisible by the index of 3. X to the 14th. If you have 14 tickets and it takes 3 tickets to go on the ride, then you're going to go 4 times on the ride with a leftover of 2 tickets. So that means that you're going to have 12 tickets in one hand and 2 leftover tickets in the other hand. Now we simplify. Seven times 5 is 35. Okay, so now we have 35x to the 4th times cube root of 5x squared. Okay, I want to do 2 more examples before the end of this lecture. So the first is example 6 from the textbook, and that would be on page 613. Part A, 18 plus 2 root 12 minus 3 root 48 plus 9. So what we're doing here is we are adding or subtracting, combination of adding and subtracting radical expressions. This would be the combining radical expressions part of the lecture. So it's easy to see that 18 and 9 can be combined. They are like terms. They are both integers. So 18 and 9 can be combined to be 27. But what about these other 2 terms? Here we have a square root of 12 and a square root of 48. You can't combine square root of 12 and square root of 48. But notice that neither the square root of 12 nor the square root of 48 is fully simplified. What that means is that we need to fully simplify before we try to combine any further. So we need to simplify the square root of 12 and simplify the square root of 48. And please do not write lines of incomplete work. If you must do scratch work, do it off to the side. But in your work, you should have full, complete lines of thought. So I'm going to go ahead and simplify within the work right here so you can see what it looks like. I will split the square root of 12 into 2 radicals. 12 splits into 4 times 3. I split the square root of 48 into 2 radicals. 48 is 16 times 3. 48 is also 4 times 12, but 4 is not the greatest perfect square that divides into 48. 16 is. Remember, you need to use the greatest perfect square that divides into the number. To simplify this further, square root of 4 simplifies into 2. square root of 16 simplifies into 4. So now, when you get to 4 square root of 3 minus 12 square root of 3, root 3, root 3, these are like terms. You can combine them. 4 root 3 minus 12 root 3. Think of it this way. 4 bananas minus 12 bananas. That would be negative 8 bananas. That was a lot of work. If you need this many steps, feel free to use this many steps. If you do not need this many steps, you can skip some steps. Don't skip all the steps. What would I do personally? I would jump from here to either here or here. One of these two should be shown as an intermediate step, okay? So there should at least be one line of intermediate work between your original expression and your simplified answer. So it should either be this line or this line. And you can show any number of lines you want. But if you wanted to streamline this process, if you can show less work, just make sure you show one of these 2 lines. Okay, let me set the board up for one last example, and then we'll wrap up the lecture. Last example. Cube root of 16x to the 4th plus 4 times the cube root of 54x to the 4th minus x times the cube root of negative 128x. This is example 7 from page 613. Each of these are like their own little problem that need to be fully simplified. So simplify each of these terms individually and then combine them. If you're going to simplify them each individually off to the side, then they need to be still simplified in an organized manner that I can read. But it's even more preferred that you simplify them within the full line of work. So let me show you how to do that. So first, I just go through and I copy down 2 cubed roots for each of the cube roots. Notice the 4 on the outside gets copied as 4. The negative x on the outside still gets copied as negative x. And now I'm going to split each of these. 16 is 8 times 2. X to the 4th is x cubed times x to the 1st. 54 is 27 times 2. X to the 4th is x cubed times x. Negative 128 is negative 64 times 2. And x to the 1st comes over here to the second radical because x to the 1st cannot be simplified inside a cube root. Okay, so the cube root of 8x cubed is 2x. And I will copy the second radical the same way. And then I have 4 times 3x with, again, a cube root of 2x. And then the cube root of negative 64 is negative 4. And again, cube root of 2x. Now let me further simplify all of this. I chose to split up the colors here because I wanted you to see very clearly that what you have are identical terms, right? You have like terms. X cube root of 2x. X cube root of 2x. X cube root of 2x. How many do you have? 2 plus 12 plus 4, which is 18. So remember that you have a bunch of recommended problems as well as the required problems. And when doing the written homework, please remember to look at the syllabus. I have changed the way that I do the assignments now for written homework. You have 3 choices, and those 3 choices are explained in the syllabus. If you have not already watched the video of me going over the syllabus, I would highly advise that you do that, because I comment along the way as to what those changes are and what they mean, and expand on them a little bit. Okay, so if you have any questions, let me know, and otherwise I will see you in the next lecture.